Good morning, everyone. My name is Yog Ramtege, and my topic is laminar flow force convection in a pipe. For the derivation of this topic, first we have to consider the laminar flow of an incompressible Newtonian fluid in a circular pipe under the action of a pressure gradient, as shown in the figure. The velocity distribution is given as this equation is given in the chapter as Vz is equal to 2 into Vz average velocity into 1 minus r by r whole square. Suppose the fluid has a uniform species A, concentration of C naught for Z less than 0. For Z greater than 0, species A concentration starts to change as a function of R and Z as a result of mass transfer from the walls of the pipe. We want to develop the governing equation for species A, concentration. Liquid viscosity is assumed to be unaffected by mass transfer. From the appendix C, the non-zero mass flux component for species A are WAR is equal to minus rho DAB del omega A by del R, and WAZ is equal to minus rho DAB del omega A by del Z plus rho A VZ. For a dilute liquid solution, the total density is almost constant. For equation 1 and 2 becomes WAR is equal to minus DAB del rho A by del R. WAZ is equal to minus DAB del rho A by del Z plus rho VZ. Dividing equation by molecular weight of species A, Ma gives NAR is equal to minus DAB del CA by del R. NAZ is equal to minus DAB del CA by del Z. Dividing equation by molecular weight of species A, Ma gives, since there is no generation of species A, rate of A in minus rate of A out is equal to 0. For a cylindrical differential volume, the element of thickness del R and length del Z as shown in figure is expressed as NAR at R into 2 pi R del Z plus NAZ at Z into 2 pi R del Z minus NAR at R plus delta R 2 pi R plus delta R into delta Z plus NAZ at Z plus delta Z 2 pi R into delta R is equal to 0. Dividing by 2 pi delta R delta Z and taking limits as delta R tends to 0 and delta Z tends to 0 gives limit delta R tends to 0 R into NAR at R minus R into NAR at R plus delta R plus limit delta Z tends to 0 R at NAZ at Z minus NAZ at Z plus delta Z is equal to 0, or 1 by R del R NAR by del R plus del NAZ by Z is equal to 0. Substituting this equation in equation 8, Vz del CA by del Z is equal to dAV by del R, R del CA by del R plus dAV del square CA by del Z square. In Z direction, mass transfer of species A is transported by both convection and diffusion. Diffusion can be considered negligible with respect to convection when Piglet number of mass transfer is very greater than 1. Thus, Vz del C by del Z is equal to dAV by R del by del R into of R del CA by del R. Force convection in mass transfer in a circular pipe of radius R. The bulk concentration is defined by CA of B, CAB is equal to double integration of VA CA R dr d theta divided by integration from double integration of VZ R dr d theta. On integrating this, in this equation we have to equate the value of CAB with this equation. On solving this equation, we get in double integration Vz del CA by del Z R dr d theta is equal to d by dz CA naught double integration Vz R dr d theta, and we will consider Q as CA naught Double integration of Vz r dr d theta. Q is volumetric flow rate. dCA by dr is equal to 0 as a result of the symmetric condition. On solving this equation, we will get Q dCAB by dz is equal to pi d dAB del CA by del r at r is equal to r. For constant wall concentration, if inner surface of pipe is coated with species A, the molar flux of species A on surface dAB del CA by del r at r is equal to r is equal to Kc CAW minus CAB. Q into integration of dCA by dCAW minus CAB is equal to pi d integration of Kc dz. Since the wall concentration CAW is constant, we get Q into log of ln CAW minus CAB in minus CAW minus CAB is equal to pi dKc z into z. Kcz is the average mass transfer coefficient. Kcz is equal to 1 by z integration of Kc dz. CAB is equal to CAW minus CAB in into e raised to power minus pi d Kcz by Q into z. The bulk concentration of species A varies exponentially. Variation of bulk concentration of species A with the axial direction for a constant bulk concentration. Evaluation of the equation over the total length L of the pipe gives Q into ln CAW minus CAB in upon CAW minus CAB out is equal to pi d KCL, where Kc is equal to 1 by L Kc integration of Kc dz. We will solve the equation 22 for CAB out. We get CAB out is equal to CAW minus CAB in into exponential of minus pi d Kc by Q into L. This equation can be expressed in terms of dimensionless number, where Stanton number for mass transfer is equal to Sh by Re into Sc is equal to Kc by Vz is equal to Kc by Q by pi d square by 4. Therefore, the bulk concentration of A varies linearly in the axial direction. This is the required profile diagram. Evaluation of equation 31 over the total length gives bulk concentration of A at exit of pipe as CAB out is equal to CAB in plus pi d Nm W by Q into L. CAB in plus 4 NaWL by dAB Ra into Sc. The rate of moles of species A transferred is given by dA Na is equal to Q CAB out minus CAB in. Substituting equation 32 in 33, Na is equal to pi dL Na W. Fully developed concentration profile. If Ca minus CAB by Cw minus CAB does not vary the axial direction, the concentration profile is said to be fully developed. Equation 35 is independent of the axial coordinate. It is del by del z Ca minus CAB by CAW minus CAB is equal to 0. It indicates that del Ca by del z is equal to CAW minus Ca by CAW minus CAB into dCAB by dz plus Ca minus CAB by CAW minus CAB dCAW by dz. Now we will solve our first question, which says that when the concentration profile is fully developed, show that the concentration gradient in the axial direction del C by del Z remains constant for a constant wall mass flux. The molar flux of the species A at the surface of the pipe is given by Na R at R is equal to Kc CAW minus CAB, which is constant. Since Kc is constant for a fully developed concentration profile, first equation CAW minus CAB is equal to constant, or we can say dCAW by dz is equal to dCAB by dz. Equation 37 simplifies to del Ca by del Z is equal to dCAB by dz is equal to dCAW by dz. Since dCAB by dZ is constant according to the equation 31, we get that del CA by del Z is equal to del CAB by del Z is equal to constant. Hence, we have showed that the concentration gradient in the axial direction remains constant for constant was mass flux. Consider the flow of a fluid with next question. Consider the flow of a fluid with constant physical properties. Show that the mass transfer coefficient is constant when the concentration profile is fully developed. For a fully developed concentration profile, the ratio given in equation 35 depends only on the radial coordinate r. Ca minus Cv by Caw minus Cb is a function of r. Differentiating this equation with respect to r, we get del Cr by del r is equal to Caw minus Cb into dF by dr. Evaluating the evaluation of equation 2 at the surface of the pipe yields del Ca by del r at r is equal to Caw minus Cb dF by dr at r is equal to r. Molar flux of species A at the pipe surface is expressed as NaW is equal to dAb del Ca by del r at r is equal to r is equal to Kc Caw minus Cab. Substituting equation 3 into 4, Kc is equal to dAb dF by dr r is equal to constant. Now the third equation. Pure water at 25 degrees Celsius flows through a smooth metal pipe of 6 cm internal diameter with an average velocity of 1.5 into 10⁵ meter per second. Once the fully developed velocity profile is established, the metal pipe is replaced by a pipe cast from benzoic acid of the same inside diameter. If the length of the pipe made of the benzoic acid is 2 meter, calculate the concentration of benzoic acid in water at the exit of the pipe. Physical properties. For water at 25 degrees Celsius, given as density is 1000 kg per meter cube, viscosity is 892 into 10⁻⁶ kg per meter square, and dAb is 1.21 into 10⁻⁹ meter square per second, and Sa is given as 737. Saturation solubility of benzoic acid in water is 3.412 kg per meter cube. We know Reynolds number is dVz into rho by mu. By putting the values, we get Reynolds number as 101, which shows that it is a laminar flow. D by L into Re into Sc is by putting the values, we get 2233 as our answer. Since the concentration of surface of pipe is constant, we get this. We get the Sherwood number as this. This equation is derived. We get this equation by derivation of another. We get this equation by derivation of Sherwood number for a fully developed concentration profile. For this, we know that 2 into Vz into 1 minus r by r square del Ca by del Z is equal to dAb by r del by del r into r del Ca by del r. For boundary condition constant wall mass plus flux, the concentration gradient in axial direction is constant. Del Ca by del Z is equal to pi d NaW by Q is constant. Sherwood number is equal to Kc into d by dAb is equal to NaW by Caw minus Cab into d by dAb. Del Ca by del Z is equal to Sh Caw minus Cab into dAb by r square Vz. Substituting equation 41 into 38, we get 2 into Sherwood number into 1 minus sigma is equal to 1 by sigma d by del sigma into sigma d theta by d sigma, where sigma is r by capital R and theta is Ca minus Cb by Caw minus Cb. Boundary condition for equation 44 at sigma is equal to 0, d theta by d sigma is 0 and sigma is equal to 1, theta is equal to 1. We get theta is equal to 1 minus Sh by 8 into 3 minus 4 sigma square plus sigma raised to power 4. Bulk concentration in dimensionless form, theta is equal to Cab minus Cab upon Caw minus Cab is equal to 0. By substituting equation 48 into 49, we get Sh is equal to 48 by 11. For constant wall concentration, we have the equation del Ca by del Z is equal to Caw minus Ca by Caw minus Cab dCab by dZ. By we have to, then dCab by dZ is equal to pi d Kc Z by Q into CAW minus CAB in into exponential of minus pi d KCZ by QC. We can write CAW minus CAB as CAW minus CAB in into exponential of minus pi d KCZ by Q. Equation 53 and 51. We get LCA by LZ is equal to 4 Kc CAW minus CA by dz. After solving the equation, we get Sherwood number as 3.663. Now Sherwood number for a fully developed velocity profile. When the velocity profile is fully developed, it is recommended to use the following semi-empirical correlations. We have these two equations at CAW is constant and CAW is and NAW is constant. Now this same equation is used in our numerical. Numerical means which question number 3. By using that equation and putting all the values, we get Sherwood number as 22.7. And considering water in a pipe as a system, a microscopic mass balance on benzoic acid gives pi d square by 4 into Vz into CAB out minus CAB in is equal to pi d L into Kc CAW minus CAB out minus CAW minus CAB in into divided by ln CAW minus CAB out upon CAW minus CAB in, which is we can say del CA into Lm, del C of Lm. Since CAB in is equal to 0, the equation 4 is converted to CAB out is equal to CAW 1 minus exponential of minus 4L by D SH by RE into SC. Substituting all the numerical values in equation 5, we get CAB out is equal to 0.316 kg per meter cube. Now our next numerical. For a laminar flow of a Newtonian fluid in a circular pipe, the velocity profile is parabolic and the equation is Vz by Vmax is equal to 0.5. In the case of turbulent flow, experimentally determined velocity profile can be represented in the form of Vz is equal to Vmax 1 minus R by R raised to power 1 by n, where n depends on the value of Re. Now show that the ratio of Vz by Vmax is given as in the table. Now to solve, in this question we have to show that for the values of n, the ratio of Vz by Vmax is 0.79, 0.82 and 0.87. Respect to the value of n is equal to 6, 7 and 10. Now we have the equation Vz is equal to Vmax 1 minus R by R raised to power 1 by n. For a flow in a pipe, Vz is equal to 1 by pi r square of A Vz into dz, where dA is equal to pi r into dr. Now putting the values of Vz and dA, we get Vz is equal to 1 by pi r square 0 to r Vmax into 1 minus R by R 1 by n into 2 pi r dr. By rearranging this, we get mean of Vz is equal to 2 Vmax by r square into integration of r 1 minus R by R power 1 by into dr. Now we have to solve this integration. For that we have to assume x is equal to r by capital R, and from this we get r is equal to capital R into x. Now differentiating this, we get dr is equal to r into dx. Now our limits are at r is equal to 0, x is equal to 0 and r is equal to capital R, x is equal to 1. On integrating this, we get Vz by Vmax is equal to 2n by n plus 1 into 2n plus 1. Now putting different values of n, we get the values of Vz by Vmax, and this values matches the values given in the question. So hence our question is proved.